Hello everyone, this is the proof of DeMoivre's theorem using induction. So DeMoivre's theorem states that, and I'm going to use Pn to denote the statement, cos theta plus I sine theta to the power of n is cos of n theta plus I sine n theta for all natural numbers. So for this first step of induction, we prove that the statement is true for the very first value of n, which in our case is n equals 1. So we're going to prove P1 is true. And P1 is the statement that the cos of theta plus I sine theta to the power of 1 is equal to the cos of 1 times theta. I'm going to overemphasize this. So 1 times theta plus I sine 1 times theta, which is clearly true. Okay, so therefore P1 is true. And then the second step is that we assume pk to be true. And you must use the word assume. Assume pk is true, i.e. that the cos of theta plus I sine theta to the power of k is equal to the cos of k times theta plus I sine k times theta. Okay, and now you want to prove that pk plus 1 is true, i.e. the statement is true when n is equal to k plus 1. So, i.e. what we want to prove is that the cos of theta plus I sine theta to the power of k plus 1 is equal to the cos of k plus 1 times theta plus I sine k plus 1 times theta. Okay, so I want to prove that, and I always use the assumption in proving at this point. So I'm going to start on the left hand side here. So the cos of theta plus I sine theta to the power of k plus 1. I'm going to break that down into the cos of theta plus I sine theta to the power of k times the cos of theta plus I sine theta. The reason I do that is the right hand side or the left hand side here of the assumption is appearing. I know what this is by assumption. It is equal to this over here. Okay, so I have this the conclusion written already because we know that the conclusion is going to be, I'll just move that down a bit. So this here is equal to the cos of k theta plus I sine k theta times the cos of theta plus I sine theta. And just to be absolutely clear where that came from, that's equal to that by assumption. And that has gotten rid of the problematic power of k. Now we're just multiplying two complex numbers, okay? So we multiply the real by the real here to get cos k theta times cos of theta. And then I'm going to get the other real part. So I sine k theta by I sine theta. That's going to give me minus the sine of k theta, the sine of theta. And then I have plus I times the cos of k theta by the sine of theta plus the sine of k theta times the cos of theta. Sorry, I ran out of room there. Okay, and then at that point you can use your trigonometric identities. Okay, so this first term here, cos A cos B minus sine A sine B, that is the cos of A plus B. So that's the cos of k theta plus theta, and then plus I times cos A sine B plus sine A cos B is the sine of A plus B. So this would be the sine of k theta plus theta. And then on the inside there, I can factor out a theta to get the cos of k plus 1 times theta plus I times the sine of k plus 1 times theta, which is what I wanted to prove. So up here above, just in pink, I stated what I wanted to prove. I started on the left-hand side and I ended up with the right-hand side. So hence, pk plus 1 is true, assuming pk is true. You always use your assumption in this step. That is why you want to get very quickly to a point where you see something that resembles a term in your assumption. Okay? And then your final step is always the same, your conclusion. I've written it in terms of p this time. So p of 1 is true, pk plus 1 is true, assuming that pk is true, therefore pn is true for all n, i.e. DeMoivre's theorem is true for all n.